Alright, so let's see if we can start figuring out some of the properties of definite integrals. Again, here's the little pack here if you want to download that and look at the interactive example, but we'll talk through it. You could also look at a graph on Desmos if you prefer. So the first one here, let's look at and think about the integral from pi to pi of sine of x dx. So think conceptually about what we're doing. So we have the graph of sine of x, which looks something like that, and we're thinking, okay, it's the area. But is it the area? Because here's where x equals pi on sine of x, is that point right there. And we're trying to find the area from pi to pi. Well, think about that. What's the width of that area? If we're using those rectangles, there is no width. And if there's no width, what's the area? The area would have to be 0. So anytime you have the same limit, I'm going to write this down, anytime the limits are the same, the area must be 0. Okay, anytime the limits are the same, the area must be 0. So that's the answer to the first one, would be 0. And let's move on to the second one here. We did previously the integral from 0 to 3 of x plus 2 dx. Let's see how that relates to the integral from 3 to 0 of x plus 2 dx. So when we found the integral from 0 to 3 of x plus 2 dx, we said that the answer here was 10.5, right? This is where we had that trapezoid shape that we were looking at. So what would it be if we went the other direction? If we went instead of, so here, let me show you the picture of what we're looking at. It was something like this right here, and this was y equals x plus 3. This was 0. This was 3. Okay. When we went with this direction, think about your change in x. You always go from the right to the left, or sorry, from the right minus the left. So that's always a positive value when you go in this direction. But when you go in the other direction, from 3 to 0, if you're starting off at 3, now you're subtracting the left value minus the right value. So each one of those delta x's aren't going to be positive. Each one of those delta x's are going to be negative. So it's the same amount of total area. The area is exactly the same. We're just doing it in the other direction. Doing it in the other direction doesn't change the value, so it doesn't change the answer of 10.5. All it does is change the sign. So what we have here is that the integral from 3 to 0 of x plus 2 dx is going to be the exact same thing as the integral from 0 to 3 of x plus 2 dx, except we have to change the sign, so I'm just going to put a negative there. And so the answer would be negative 10.5 in this case. So swapping the limits doesn't change the value, it just changes the sign. Okay? Let's look at this next one. This next one's very helpful sometimes, and believe it or not, it is. Okay, it says in figure 5.25, the larger region can be divided at x equals c into two subregions whose intersection is a line segment. Because the line segment has 0 area, it follows that the area of the larger region is equal to the sum of the two areas of the smaller region. So what did they do? Look at that red area that they have there. What they're saying here is it's the same thing as, the red area is the same thing as finding the blue area, the first half that I just shaded, and the green area, the second half that I just shaded. So what they're saying is instead of finding that red area, what we could do is we could find the blue area, and then we could find the green area, and then we can add them together. So what was the original one? The red area was the integral from a to b. So that would be right here. And what we're saying is that's equal to the integral from a to c, the first one, plus the integral from c to b, the second one. So if it helps you, you can break up a definite integral and find an integral of one part and then the next part. That's going to be super helpful when you see things like, I don't know, how about the absolute value of x? And you want to find the area of the absolute value of x? Well, it's going to be helpful to find the area of one piece first, the area of a second piece second, and then add those two pieces together. Okay? So that can be a very, very helpful theorem for you.